All right. I will begin. Heavenly Father, we thank you for this day. And Lord, I thank you for the students. Just ask you to be with us today. Help us to glorify you what we do, Lord. In your name I pray. Amen. Joshua has worried me. Yeah, we're still good. I was afraid you'd touch that thing, but yeah, it's all good. All right. So, you got your homework. Where's my stack of homework? Where did it go? Oh, you guys are already up there? Excellent. All right, so let us continue with our exampling, if you will, of things. One thing I should talk a little bit about before I do any much more in terms of, I'm going to calculate more flux integrals today. But to start with, I thought I should spend a little bit of time on so-called scalar surface integrals. Well, that's not, yeah, well, what do you call these stupid, I don't know what to call these stupid things. It's the integral of a function over the surface. What I mean by that is you're given some function, a scalar function, then we talk about the integral over some surface of f ds, right? And I define that, the integral over the domain of the parameterization. You take your function, you shove the parameterization into the function, and then you multiply by ds, ds being the norm of partial x partial u cross partial x partial v du dv. So this is the so-called scalar surface integral. What it is it's adding up values of f over the surface. So here's an interpretation. If f, for example, was the mass per unit surface area, so like the mass per unit area on the surface, we could say f is dm ds. Now usually, at least in my way of thinking, I call this sigma. It's a surface area density. Well, it's a, surface density rather. It's a curved area density. I mean, we've talked about this notion before for a flat thing, right? But if you were to calculate, the integral of sigma ds, what would that be? I mean, that is really the integral over s of dm. So see, that would be the total mass. To get the total mass of a surface, you'd integrate the mass per unit surface area, and that would give you the total mass. You probably can guess where this is going. So if you've got some surface, right, like these, so that's your surface, you can calculate the total mass of the surface if you give it its mass per unit area, and you can do other things. Like you could calculate its center of mass, right? What would the center of mass, the surface? I mean, in my picture, roughly something like, depending on how curvy this is, maybe it's, I don't know, it's like in here somewhere. That's supposed to be below the surface. I can't draw it worth anything. Anyway, somewhere there's a center of mass, x bar, y bar, z bar, right? How would you calculate that center of mass? 1 over m integral of x ds. You basically take the weighted average of x over the surface. That gives you the average x value on the surface. That's your center of mass coordinate number 1. And I think you know what we're going to do from here, right? I mean, we could say this, x sub I, also do sub j, for j equals to 1, 2, 3, using x equal to x1, y equals to x2, z equals to x3. There, I saved myself some writing. Haha. Anyway, the same formula, right, with x bar, with y bar, with z bar. What if you were to calculate the moment of inertia about the z-axis for the surface? If you want to think about the surface being, like you could, for example, think about the surface being something like a, I don't know, it could be a sphere, for example. And maybe the sphere is not a solid sphere, but like a spherical shell. So if I could do a cutaway, just a spherical shell, right? I mean, like a basketball, right? What's the moment of inertia for a basketball? You know, if I had one, you spin on your finger. What's the rotational kinetic energy of a basketball? I mean, 1/2 I omega squared, right? What's that I for a basketball of mass m? Well, assuming that the basketball is uniformly constructed, we need to find the mass per unit area, right? And calculate its moment of inertia. How would you calculate the moment of inertia? Pretty simple. Moment of inertia with respect to the z-axis for a surface, what we do is we calculate the integral over the surface of, well, x squared plus y squared dm. That's exactly what we did previously for a solid, except instead of having an integral over a surface, we had an integral over a volume, right? We calculated, for example, the moment of inertia for a solid sphere before by doing a triple integral, right? Remember we worked it out, it was 2/5 mr squared. So what would this mean? This would mean you integrate over the surface x squared plus y squared. Your dm, you do sigma ds in this context. Let me be less ethereal. Let's actually work out the basketball example, okay? Basketball, radius r, mass m.
Using a sports example? Oh my.
A sports example. Turn off that camera. What is it? What's that? Attendance. Ah! Dang it. It's very frustrating.
Frustrating sports.
Yes, I was about to talk about the basketball ring and the fact that we could have Ted Cruz as a president right now, but let's not talk about it. Anyway, all right, so name was Caleb. Okay, make greedy for points. Let's see here. All right. See, this is the real cost of this. I hate doing this. Fine, you guys enjoy it. I guess it's worth it.
But you have to be off to stop it.
I could stop. That is true. This is, but it is a rule that I made up, and
Now that it started,
you know, if that guy was not to take Daniel out of the lion's den, who am I to change the rule about this? All right. All right. Teach me to let you do the camera. All right, got that over with. All right, now there's something here that we need that I haven't proved yet, which is in order to figure out the sigma for the basketball, we actually need to know the surface area of a sphere. What's the surface area? So, pre-example. Pre-example. What's the surface area for a sphere? We can work that out, right? That would be the integral over the sphere of radius r of ds. Remember? We worked out what that is. Well, we didn't work this out yet, but we will here in just a second. What was ds for the sphere? That's what we worked out. Remember? It was. So the sphere goes over the full range of 0 to pi, 0 to 2 pi. You got yourself an r squared sine phi d theta d phi. That's the surface area element for the sphere. And so we can pull r squared out, And then we've got integral from 0 to, I might have done this. I don't know. I can't remember. Did we do this already? I don't remember. I don't think so. We've done stuff like it, but not it. I mean, we've seen these integrals before, but that integral works out to r squared times 2 pi. In other words, the surface area of a sphere is 4 pi r squared. I need that for my basketball example because I want to describe to you what is the surface mass density for the basketball of mass m. What is it? So sigma, right, should be the total mass divided by total surface area, right? That's only true for a uniform sphere, uniform spherical shell, right? So to a kind of decent approximation to basketball's that, right? This would be better if I was to say a dodgeball, right? It's like more of like a perfect sphere, right? Until it hits you in the head. But let's see here. So m, and we just figured out 4 pi r squared. So there you go. That's my mass per unit area for this basketball. I want to calculate the moment of inertia. So what am I supposed to calculate? I'm supposed to calculate the integral. Well, I'm not going to have enough room here. I'm going to start over here. So I'm supposed to calculate the moment of inertia. It's the double integral of x squared plus y squared sigma ds. Right? And so let's see here. We've got integral from 0 to 2 pi, integral from 0 to pi. And then I need to remind you guys what is the parameterization for the sphere that we used here. We had x equals to r cosine theta sine phi, y r sine theta sine phi, and z r cosine phi. So what's x squared plus y squared? Oh, fine, I'll just be lazy and write it down. R squared cosine squared theta sine squared phi plus r squared sine squared theta sine squared phi. And then I got my sigma, which, you know, this sigma is just a constant, so let's just leave it sigma. We'll put this in eventually, but since it doesn't give me joy to write m over 4 pi r squared 6 more times, let's just call this sigma, and remember that we can simplify it back to this eventually. All right? Sigma. In fact, let's be lazier. Sigma. Keep it out of trouble out front. And then what we got? Oh, the ds. The ds, remember, is r squared sine phi d phi d theta. Now, you guys can tell me, this is actually what? And what's a lazier way we could have done this calculation? A lazier way we could have done this calculation is to notice that this is in fact r squared, which is rho sine phi squared, which in this case is r squared sine squared phi. R squared sine squared phi is exactly what this simplifies down to. Because cosine squared plus sine squared is 1, and you got a common sine squared phi. So it is completely unsurprising that that simplifies to r squared sine squared phi because of the interrelation of spherical and cylindrical coordinates. So what we got in total, we've got an r to the 4th. We got a sine cubed phi d phi d theta. I feel like the integral of sine cubes works out to 4/3. But I'm not sure. We did it a few weeks ago. So we have the integral over theta. There's no theta here. The r pulls out. We get 2 pi sigma r to the 4th integral from 0 to pi of 1 minus cosine squared phi sine phi d phi. And so what's that? Well, we can let u equal to cosine phi. That makes du minus sine phi d phi. That makes u of 0 equal to 1. It makes u of pi equal to minus 1. So with that u substitution, we got an integral from 1 to minus 1, 1 minus u squared times minus du. Which is what? Great. So we've got u minus, or rather minus u plus u cubed over 3, evaluated from 1 to minus 1. Which gives me what? Two-thirds minus a minus two-thirds. Aha! A useless fact was recorded in my brain. This integral does work out to 4/3. Yay. So that, in fact, does work out to 4/3. And what do we got? We've got 2 pi. What was my sigma? M divided by 4 pi r squared, right? Times r to the 4th times 4/3. Okay, so what does that work out to? The pi's, they be canceling. We got 4's cancel. I see a 2/3. M. It looks like 2/3 mr squared, yeah? Now we worked out for the, so this is for a spherical shell, right? So if I was to sort of do it like, I mean, it's a shell versus the solid sphere. So the solid sphere of the same mass and the same radius has a moment of inertia of what did we work out? 2/5, if I recall correctly. Is that right? Did we work it out? Was it 2/5, wasn't it? Was it 3/5? 2/5?
Did we do it yesterday?
No. It was a while ago. It was when we were doing triple integrals. Around when I introduced spherical coordinates. Spherical integration. Well, this much you should be able to anticipate. Should the moment of inertia be larger for the solid sphere or for the spherical shell? No, it should not be the solid. It should be the spherical shell because you get more rotational kinetic energy if you've got a given mass rotating when it's like a shell. See, because more of the mass is further away from the rotation axis, which corresponds to more rotational energy, everything else being equal. 2/5. And as you can see, 2/3 is greater than 2/5. Yeah. The ultimate, if you wanted to, make something that has most rotational kinetic energy possible for some sort of surface, what you should do is like a cylinder, right? Because if you had a cylinder rotating like this, you have all of the mass, the maximal distance for, if all of the masses at radius r, the moment of inertia there is just mr squared. Because it's all distance r from the rotation axis. That's like the biggest moment of inertia you can get for a given radius shape. Yeah. But anyway. All right. Well, anyway, I just wanted to show you a sample calculation. This is how you do a scalar surface integral. You notice that what's missing here is there's no like PQR vector, right? You just take the scalar function that you have, you plug in the parameterization for the surface, multiply it by ds, and then do the integration. That's it. So the most important example, of course, of the scalar surface integral is just the surface area calculation. Let's see here. Well, I'll do one more of these. Set up surface area of paraboloid. Let's look at the paraboloid y equals to 1 minus x squared minus z squared. Above the xz plane. So here's a picture of what's going on. So this is, where's the vertex, if you will, of this paraboloid, this downward opening paraboloid? It's when x and z are both 0 and y is 1. So that is like here, let's say, right? And I said it's above the xz plane. So you get, parabola like this, you get a parabola like that. This thing. So it's basically one of these deals, like that. That's what we're looking at. I want to calculate the surface area of that. So how do I do it? I really just need to come up with a parameterization of the surface, right? It's not one of our standard examples. We have to go back to scratch. Yeah? What's the parameterization of that surface? Can you tell me? If you want, you want me to use u and v, or you want me to use letters that are more representative of what they are? The second one. So may I suggest that x and z are pretty good parameters for this surface, right? Because if you give me x and z, it puts you someplace here, like x comma z. Oh, no. Z does not go in the y spot, but x comma 1 minus x squared minus z squared comma z, right? That's a typical point on this surface. So the parameterization, if we use y and z for my parameters, parameterization looks like x. Oh, good grief. Yay. So let's say use xz. So I got x comma 1 minus x squared minus z squared and z. There you go. First order of business, I've parameterized the surface. At this point, now we have a clear path. We can calculate the ds. How do we do it? We need to find the normal vector field, right? And calculate the length of it. So partial x, so the normal at xz is partial x, cross product with partial x, partial z, which is the determinant x hat, y hat, z hat. You calculate these partial derivatives for me. What's partial x, partial x? I got a 1. I'll take that 1. What's next? Ooh, I'll do the 0. There we go. How about the middle one? Negative 2x. I'll accept that. And for the third row, I'll start 0. Haha. Oh, and I'll do this one. 1. But the middle? Negative 2z. All right. And then, okay, so then we got to calculate this cross product, right? So what we got? Looks like minus 2x, minus 1, and minus 2z. Thus, ds, which is, by the way, the length of the normal vector times, in this case, dx dz, is the square root of 1 plus 4x squared plus 4z squared dx dz. That's the scalar surface area element for this paraboloid. And so, and by the way, what's the domain? At this point, you see, all of a sudden we need to know the domain of the parameterization, right? That wasn't given to us here. We have to figure it out from the geometry, from the problem statement. So this is as far as she goes, right? Like this. That's the intersection of the xz plane and the surface, right? That's where what? Y equals to 0. So if we set 0 equals to 1 minus x squared minus z squared, that describes that intersection, which is to say that we've got 1 equals to x squared plus z squared, right? So the domain here, in retrospect, is in fact x squared plus z squared less than or equal to 1. That describes the domain of the parameterization. And that's important because we need to know the domain of the parameterization in order to calculate the surface area. So let's do it. Surface area equals integral. I need to give this name, a paraboloid, a name. Marge. Okay, so we take the integral over Marge. I mean, I give too many males names. I'm trying to be less sexist, so there you go. Marge. Actually, who am I to judge? That could be a man. I can't say. We don't know anymore, these kinds of names. What name? What's a name? Anyway, so I'll see if I'm not careful, I have to edit this video. Curses. I don't think I'm there yet. I'm not there yet. I'm working on it. Let's move on before I have to edit. All right, integral. You have to be careful. I don't want to offend people. X squared plus z squared less than or equal to 1. That describes the domain of the parameterization. And we're supposed to integrate ds, which is in fact, boots on the ground formula right here, 1 plus 4x squared plus 4z squared dx dz. I will remind you my problem statement had a very important phrase, which means we are done. Although, now that I've written that, I think I can do it. Want to see how? Let's do it. This we can actually calculate if we use modified polar coordinates. I'll do it over here so we can all see it more cleanly. So what you want to do is let y equals to little r cosine theta. I'll tell you, let's just use a beta. Forget about the theta. Oh, beta doesn't get enough airtime in here. Let's use beta. All right. And let's not use r. Let's use s. S and beta. All right. So trying to calculate the integral over x squared plus z squared less than or equal to 1, square root 1 plus 4x squared plus 4z squared dx dz. So my suggestion is we let x equal to s cosine beta. We let y, oh, I'm an idiot, z equal to s sine beta. You can calculate partial x z partial s beta is, the determinant. Well, anyway, through the usual, fine, x sub s, z sub s, x sub beta, z sub beta, and so what does that give us? Cosine beta, sine beta, minus s cosine sine beta. I'm regretting this level of detail. S cosine beta. Of course, we get s cosine squared plus s sine squared, which is to say that this Jacobian works out to s. This is not surprising because these are just modified. This is just other I'm just using s for r and beta for theta. Of course, the Jacobian works out to the r, which is here the s. This is not surprising. On the other hand, what is this? In terms of these modified polar coordinates, this is nothing more than 0 to 1 for s, right? So in the s beta coordinate system, this integration becomes 0 to 2 pi, 0 to 1. What's this? This is the square root. Indeedly. 1 plus 4s squared, yeah? And what's my area element? It's actually s ds d beta. So you see what we got is we've got 2 pi, the integral of s times the square root of 1 plus 4s squared ds from 0 to 1, which is something we can do because that is a u substitution. Let this be u, right? Then du is what? 8s ds. So what we got here is 2 pi integral. Let's see if I change the bounds. What do they change to? 1. Plug in s equal to 1. What do you get? 5. Yeah. And that is apparently 1/8 square root of u du. So that gives us 2 pi over 8. And let's see, 1/2 plus 1, 3/2, so 2/3 u to the 3/2 evaluated from 1 to 5. So we got here, we got ourselves a pi over 6, 5 to the 3/2 minus 1. There you go, that's the surface area of this paraboloid. But I'm just telling you, if I don't think hard, if I run out of time, I don't have time to just check the test question and make sure it is easy to calculate, I will hedge my bets and say just set up a surface area integral. Because largely speaking, surface area integrals you cannot actually hack. This is actually pretty fortunate that we could do this integral. Because look at what the surface area integral involves. What does it involve? Square root. Square root of sums of squares. Of weird stuff. There's really no guarantee that stuff like this ends up being integrable by us in terms of elementary methods. In contrast, in very marked contrast, the flux integrals did not involve a square root. They appear to at the start, but they don't, because that norm of the normal vector cancels out, and we just end up calculating the dot product of the vector field with the normal for the flux integral. So flux integrals end up being easier to actually calculate, right? Despite the fact that I think conceptually what a surface integral is kind of simpler, right? You're just adding up like density over a surface to calculate the net mass or the net charge of some sort of like thin bendy thing. That was sudden. Let's see here. All right, so let's move on. All right, so I just wanted to, I probably have assigned a homework or two with this in it, so I wanted to make sure that you know what it is and how to calculate it. I think I've told you this story about center of mass and total mass in how many different contexts now? For a curve, for a flat shape, for a volume, right? Now for a surface. For all of those different things, in principle, we could calculate center of mass, total mass, and moment of inertia about some rotational axis if you wanted. That's kind of neat. It's more neat if you're a physics major, but you're not a physics major, so there you go. Oh, I can leave this up for a bit. So. All right, so let's go back and do some more examples of flux integrals, aka surface integrals. Surface integration of vector fields. I wanted to do one that's kind of got a lot of moving parts, but is relatively simple, each part. So I think a good one to work would be something like this. Suppose we're looking at the unit cube. So the unit cube. So here I'm going to think of the one. So this point, we just tell you a few points. If I tell you one point, actually it's fixed what it is. This point right here, I want to be 1, 0, 0. It's a cube, right? So now you know the rest. So if this is a cube and that point's 1, 0, 0, what's this point? 1, 1, 0. Up here you've got 0, 1, 1. This guy, 0, 0, 1, etc. All right. There are 6 faces to the cube, right? Let's write down a good choice of parameters and the surface area element for each face. Okay? Make a table since there's 6 things. Just keep things organized here. So, face, parameters, and finally the S vector. So I need to come up with a way to label the faces, right? So let's say top, base, right, left, and then front, and then back. And I say parameters, but let me add another. Let me say parameterization. Stupid word. Parameters. We need a better word for this in English. Parameterization. Face. Parameters. I'm adding a column. Sorry. All right. So let's start out here. Top. And if you don't, oh, fine. So for the top, I would use x and y for parameters. The parameterization I would use would be x, comma, y, comma, what's z on the top face? It's just 1, right? And what's my ds? My ds is nothing more than dx, dy, z hat. Right? Because if you picture it, it's like these. Got some little, dx like, dy like this, dx like that, and here's your ds. You can picture it. Yes, we could go through the trouble of calculating the cross product of the parameterization partial coordinate velocities with x and y respective. It would work out to 1. The magnitude of that vector would work out to, well, it would work out to z hat. Anyway, so this is what it is. But I think you can see from pure geometry alone that that should be what ds vector is, right? How about the base? The base face. Again, we can use x and y for parameters. And if the parameterization is, x, y, 0, actually, I should be careful. If I want the, now here's the question is, how do you want to orient the base face? let's declare that we're looking for outward-oriented normals. All right? So that means what I need for the base face is actually minus dx dy z hat. That's what I want, right? Because I'm thinking, you got your little dy, you got your little dx, right? And this should be the direction, right? Minus z hat should be the direction of the normal. That means that the order of my parameters should not be x, y. Technically speaking, I should do yx. Why am I saying that? Because partial, partial x, partial y cross partial x here would be y hat cross x hat, which would be minus z hat. If I order the parameters x, y for the lower face, then I wouldn't get the right normal if I want a downward pointing normal. Anyway. Let's see here, what's next? Left, all right. I guess that's right. No, wait a minute, correct? Sorry, I'm an idiot. So left has, I would use parameters, let's see here, I got to think about this. I want the normal to go in the minus y hat direction. So I should do like parameters of x and z. Because x hat cross z hat is minus y hat. So here it goes. We got, is that right? Oh yeah, y is equal to 0 there, right? So x, 0, z. And what we got? We got minus dx, dz, bless you, y hat. All right. The right. We again use, this time we'll use z and x. And again, x1 z. This time's dx, dz, y hat. No minus this time. Because this is what ds looks like outward pointing here, right? Little dz here, little dy there. Yeah. Next up, top. Oh, sorry. Yeah. Front. We want it to be coming out at us like this, right? That's the x hat direction. We're going to use y and z for the parameters there. Because y hat cross z hat is x hat. So that's going to work for us. So we got 1, y, z. That's the formula for the parameterization. We got ourselves a dy, a dz, an x hat. There you go. That's my ds vector. And then finally, the back. Again, we'll this time use zy because we want it to point the opposite direction. We got 0, we got y, we got z. We got a dy, dz, x hat, but there's a minus. Because again, it's got to be pointing out the back. We good? Now, we can do things like calculate the flux of the vector field x squared, x squared, x squared through the cube. Let's do it. Let's calculate. We've got everything we need. We're going to use these things to continue this problem. So let's find the integral over the cube. Cube. The one I just talked about there, unit cube. Well, it's not really the cube, it's the boundary of the cube, isn't it? It's really the boundary of the cube that we're finding the flux through, is it not? When I think of the cube, I really think of, well, I don't know, this is the question. Do you mean the solid cube? Or do you mean the surface of the solid cube, which is also, we refer to both as a cube, if you think about it, in our common language. Would you say a cubical surface, or would you just say cube?
Box.
You'd say box.
No.
There we go. That's good. But even a box, do you mean it's full or not? It's not. Empty box. All right. Well. Anyway, there is some danger for confusion here. Like, do you mean a spherical shell, or do you mean a solid sphere when you're talking about a sphere? I personally find myself using the word interchangeably. if I'm not careful. So for me, just saying a sphere is somewhat ambiguous. I try to remove all that kind of ambiguity on tests in here, but if you're ever not sure, you ask me. This is much more dangerous in physics. We try to use the word spherical shell to make you alerted to the fact it's like a spherical shell, as opposed to a sphere, which is often meaning a solid sphere. But I prefer the term ball. But even there, like the basketball, it's not, well, rubber ball is better. I don't know. Anyway, I'm going to shut up. So, here we go. X squared, x squared, x squared, dot ds. Let's work it out. So what is that flux? Is got 6 pieces, right? In principle, the top, the bottom, the left, the right, the front, the back. All 6 faces can contribute flux. Let's work them out. So the integral over the top, right? So what we got? What's our x squared for the top? It's x squared. So there you go. Sorry. So this is kind of the contrast of white on white right now. Yeah. Well, but our ds was interesting. It was what? dy. Oh, I'm sorry. I can't do math. I can't. It's right there. I could read it. dx, dy. Good grief. I'll get it eventually. Z hat. dx, dy. So what's this integral here? I mean, what's that dot product, first of all? What does the dot product leave us with? Come on. Stop that. Yep, just x squared. So we've got the integral. And what's the domain of the parameterization there, by the way? What do this x and y range over on the top face? They range x equals 0 to x equals 1, y equals 0 to y equals 1. It's just the unit square, right? So 0 to 1, 0 to 1, like that. And this one's pretty nice, right? We really just have integral from 0 to 1 of dy, integral from 0 to 1 of x squared dx. So what's this give me? This gives me 1/3. 1/3. Next, integral through the base. What do we get? So I'm going to go ahead and do the evaluation at the base. What on the base we have what? Oh, it's still x squared, right? In fact, is this calculation even going to be it's just marginally different, right? We don't have z, we have minus z hat, yeah? So we get the double integral 0 to 1, 0 to 1, minus x squared dx dy, minus 1/3. Right? Next up, let's do the integral over the left side. What's that look like? What is x for the left side? Eventually this will get interesting down in cases 5 and 6 of the evaluation. I'm sorry, but it is what it is. I should have made a more interesting vector field. Oh well. No, it's too late. It's too late. I can't do it. Let's see here. So we're supposed to plug in x squared, x squared, x squared. And we take the dot product with what this time? Minus y hat. And this time what? dx dz. So we're left with the integral from 0 to 1, integral from 0 to 1 of minus x squared dx dz, which again works out to minus a third, right? Likewise, the integral over the right face is x squared, x squared, x squared, dot product with y hat dx dz, right? And that gives us the integral from 0 to 1, integral from 0 to 1 of x squared dx dz, which again works out to 1/3. So it looks like the flux through the top to base and the left and right equal and opposite canceling out. Starting to feel like this might work out to 0. Does it? I don't know. Integral front face. Finally, something interesting in terms of the mechanics of the calculation. See, because we have to evaluate the vector field at 1, y, z. Right? So what happens when you evaluate the vector field x squared, x squared, x squared at 1, y, z? We're putting x equal to 1. So what is it? It's just 1, 1, 1. Dot. And what's my ds? My x hat dy dz. So, well, this is going to be the integral from 0 to 1, integral from 0 to 1 of dy dz. Well, that's just 1. All right. And finally, what's the integral on the back face? Yeah, 0, 0, 0. You got it. Minus x hat dy dz. So that works out to 0. So the net flux through the cube is the sum of these 6 fluxes, right? And that apparently is nothing more than 1. As long as we've gone through all this trouble, let's look at the flux of a more interesting vector field through one of the faces, all right? Just to get more experience with this calculation. So you guys, you give me any vector field that you want as long as it only involves polynomial formulas of x, y, and z for the components, all right? Yeah.
Where did the x squared x squared x squared come
That was given.
from?
Yeah. Yeah, I made it up. Like I'm asking you guys to make up a new one. Vector field f x, y, z equals to, you guys tell me. X, y? I like it. What's next? No, I said no, none of that. I mean, we could, fine, you know what? There we go. All right, and then what's the next? X to the 10th. X to the 10th. All right, there we go. I think you have. I think we have had enough calculus 2 to do this one when the you know, the whatever hits the fan. Let's see here. So let's look at face. I feel like the base face is a good one. Let me make this. I'll tell you what, I'll take your cosine and raise you a cosine to the 113th power. There you go. So let's calculate the flux through the base face of this f. All right, so what we're supposed to do then, here's the deal, integral from 0 to 1, integral from 0 to 1. We take f, we evaluate it at the parameterization of the base face, which is what? X, y, 0. Right? And we take the dot product with the ds, which in this case is 0, 0, minus 1, and then dx dy. So looks like Mr. x to the 10th is the only one that actually matters, because what we actually have here is what? Xy cosine to the 113th power of 0 and well, 0. Wait a minute. No, not 0. I'm an idiot. X to the 10th dotted with z hat, well, minus z hat, 0, 0, minus 1. So what's that work out to? Dot product kills off the first two interesting components. And we're just left with integration of minus x to the 10th from 0 to 1. And that is minus 1/11. Questions? So if you're given a shape that is not one of our standard examples, namely what? Sphere, cylinder, cone, z equals f of xy was a standard example for us. So we derived the general formula for the surface area element and the vector surface area element. I mean the vector, ds vector, the other day. So if it's one of those, you can go to the notes and you can just rip off from what we've already done what is ds vector and go from there, right? But if it's a new shape, if it's one that we don't have sitting on our list of standard examples, we have to think through it. We have to think about what's the parameterization for the surface and come up with what ds vector is. So sometimes you don't really need to do all of the calculus that I've shown you. Sometimes you can just see from raw geometric intuition what these formulas should be. You can derive every last one of these by calculating the normal vector field. But I don't think you need to. I think for a cube, you can just look at it and go, you know what? ds vector on the top, it should be dx dy z hat. All right? Anyway. But I think it would be healthy for us to do another example that's kind of based on our catalog of standard examples. I want to show you how we can modify them a little bit, just in terms of, instead of looking at like a whole sphere, look at part of the sphere. Let's calculate the flux of a vector field through like a hemisphere, right? So remember this for tomorrow, that the integral of x squared, x squared, x squared over the cube was 1. Because tomorrow, I will show you how to do this example in 3 minutes. Remind me to do that tomorrow, please. No, no daily quizzes this week. I'm just going to keep teaching you. Next week, we'll get back to quizzing galore. But this week, in fact, tomorrow, if you come tomorrow, I mean, I hope you come tomorrow, or at least watch later, I will pretty much finish the course. At least the meat and potatoes of the course, the part I mostly test you on. Modulo the proof, but I will state the 2 major theorems for the course tomorrow. Because we've been doing these surface integrals for a while, so we're hopefully getting to the place where we can at least understand the 2 central theorems about surface integrals, namely the divergence theorem and Stokes' theorem. But I'm going to wait till tomorrow to do those, because I will make sure that we have as much understanding of surface integrals as we can before I state them. So here's another example. Suppose you're looking at a hemisphere, right? So oriented in the Vine Center, right? There you go. And we're going to look at the vector field F equal to z hat. So it's kind of a boring vector field, 0, 0, 1. But let's calculate the flux of this vector field through the hemisphere. So it's an open hemisphere, all right? I'm not including the base, the disk, right? So basically we have ds